All right, so we're basically on the last section of chapter 10. Um, Basically, the last couple of lectures, we were focusing on how to represent functions as power series, right? So right now, I made a list, or we made a list of sort of well-known Maclaurin series for certain functions, and so we have these right now. Okay, and so the last section, chapter or section 10.10 is all about sort of how do we use this, right? So why are we doing power series um, to begin with, right? So what's so important about power series? And that's what we're going to be talking about in 10.10. Okay. And so, okay, just also you're that now. Okay. All right. 10.10 applications, power series. Okay. And so for this one, let's use a sort of a calculus example, right? So what's an application of a power series that involves calculus? And so here's example number one. And so suppose I want to integrate e to the negative x squared dx. Okay. And so this function is actually not integrable, right? So I don't care what technique you learned in chapter 8, okay? And we actually remember we went through a lot of techniques on how to integrate. This is something you can't integrate. Okay, so this is something that you cannot actually integrate um, in this version. So now you might ask, oh, that never shows up in sort of an application or in real world, so there's no really need to use this or integrate this function. And so this is actually your, so if you've taken statistics, this has something to do with your normal distribution. So, so this is equivalent to doing the normal distribution and the probabilities using normal distribution. So this is actually used for something. And so now the question is, how do you integrate something like this? And so one version or one way to integrate this is to write the power series for this one, and then essentially integrate that said power series. So now recall e to the x, right, is 1 plus x squared over 2 factorial, x cubed over 3 factorial, dot, 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 which is the power series from 0 to infinity of x to the n over n factorial. Okay, so that's the e to x. So now e to the negative x squared, I'm just replacing x with negative x squared. So e to the negative x squared would be 1 um, minus x squared plus an x to the fourth over 2 factorial, right? Because when you plug in square here, squared squared would be to the fourth power. This would be a minus x to the 6 over 3 factorial. And so when you do the summation notation, sorry, equals, replace this with negative x squared, you're going to have a negative 1 to the n, x to the 2n. Does it look like a 2? Okay, all over n factorial. And so this is now what you integrate. So instead of integrating e to the negative x squared, which we can't, this is now what you integrate, which is a polynomial. And so we know how polynomials work. And so to integrate a polynomial, it's simply doing the power rule. Okay, and so let's go ahead and do that, right? So this will now be equal to the integral of 1 minus an x squared plus an x to the fourth over 2 factorial minus x to the 6 over 3 factorial, and then dot, 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 dx. And just to make this nicer, let me change that. to the 6th power. And then do the power rule, right? So integrate. So integral of 1 is x. This would be a minus x cubed over 3 plus an x to the 5th over 5 times 2 factorial minus x to the 7 over 7 times 3 factorial, and then dot, dot, dot. Now in summation notation, n equals 0 to infinity. So if I integrate this, I'll have a -1 to the n power. And so again, the x is your variable, right? So integrating this, you're going to add a power of, or you're going to add 1 to the exponent. So x to the 2n plus 1. And then you divide by that exponent, 2n plus 1. And then remember, you still have the n factorial. And so this ends up becoming your power series. Any questions on that? Any questions on it? All right, so I want you to try one. Okay, so another function, or another function that is not integrable in terms of techniques that we do is this one. Okay, so example number 2. So the integral of cosine x squared dx. And so go ahead and integrate that. Let me pause the recording. All right, so again, since I am integrating, if you want to just use the summation notation already, right, and so you can certainly do so. So cosine x squared, right? Let me do cosine x first. So cosine x. So cosine x is the one with the even power. So it's the summation from n equals 0 to infinity, -1 to the n, x to the 2n over 2n factorial. So that means cosine x squared is the summation from 0 to infinity of -1 to the n, x to the what power? So it's going to be x to the what if you replace x with x squared? Not x cubed, because there's an n. So you're replacing this with x squared. So this is what you have. It's x to the 4n, right? Because you're going to end up multiplying those. So you get 4n, and then the bottom stays the same, right? Because you're just replacing the x. So it'll be 2n factorial. And then now this is what you're integrating. Now remember, you're integrating with respect to x. So x is your variable, at least for the integration part. And so now when you integrate, okay, the summation would be from 0 to infinity. So everything else stays the same. So you get -1 to the n. It will still be a fraction. You'll still have the 2n factorial. So this would now be x to the what power? So when you integrate, this would be x to the power. So using your power rule, it would be what? 4n plus 1, right? And then you divide by that new power. So that means 4n plus 1 will go to the bottom. And there is your answer, right? So that will be it And there is your answer. That one. Okay. Questions? Any questions on it? Okay. All right. So if there are no more questions, right? So we're sort of going to move on to the next application. And so remember, the main application is always representing a function as a power series, right? That's really what we're after here. So now the other part of this is, oh, okay, I can do that, I think. Okay. All right. So the other thing on this is, um, obviously when you actually approximate a function, you don't want to use infinite series, right? You don't want to have infinite terms on them. So you want to have, or you want to use a finite number of terms to approximate your function. So now the question is, how far do you go, right? So how many terms do you use for your polynomial to approximate your function? And well, that will depend on how much error you want to have on your approximation. So the lower or the smaller your error, or the smaller the error you want, then the more terms you're going to have to use. The less terms you use, then the error increases. And so that will all depend on error. So which means we have to talk about errors in terms of Taylor and Maclaurin series. So here are the errors for Taylor and Maclaurin, because basically the same thing, except Maclaurin, the center, which is A, at least your book's notation, is 0. Okay. And so this, by the way, is called the remainder estimation theorem, or Taylor's theorem. Okay. And so basically the error, do I want to put absolute? Yeah, let's do. So the maximum value, or sorry, the absolute value of the error, okay, is less than or equal to, okay, m, and we'll talk about what m is, times x minus a to the n plus 1, okay, all over, okay, n plus 1 factorial. Okay. The m is basically the maximum value of the n plus 1th derivative of your function, okay, on the interval. Okay. And so m is the maximum value of your nth plus 1th derivative. Okay, now so this is Taylor. The Maclaurin version, essentially it's the same thing, it's just that the a would be 0, so the error is less than or equal to m uh, x to the n plus 1 over n plus 1 factorial. And so now, if you sort of put this in for your m, and sort of look at this in terms of your power series, basically these are essentially the n plus 1th term of your series. So it gives you sort of an upper bound on what is the maximum error of your um, power series. And according to this, essentially the first term you drop. So you keep n terms, and then the first one that you drop is the n plus 1th term. And so that will give you sort of an upper bound of what your error could be based off of that. Okay. And so example number one, number three. Okay. So evaluate the integral from 0 to 0.1 of e to the negative x squared dx such that the error is less than 10 to the minus 6 power. So which means I want to find this definite integral. And as I already mentioned before, right, this is something you can't integrate. So you want to be able to find the value of this integral so that the error is less than 10 to the minus 6. Okay. And so now, okay, the first thing you want to do is obviously integrate, and we already did this one, right? So recall the integral. Is this one, right? So it's the odd powers, right? And then divided by those odd powers and then the factorials, right? And so these, oops. So it's x minus x cubed over 3 times 2 factorial, okay, plus x to the 5th over 5 times 3 factorial. Sorry, this is just times 3. So this is just times 3. And then this is 5 times 2 factorial minus an x to the 7 over 7 times 3 factorial plus x to the 9 over 9 times 4 factorial. Okay, and then dot, right? And then you are evaluating from 0 to 0.1. So the first thing I want to do is figure out where I'm going to cut things off, right? So for which one of these terms is the error going to be less than 10 to the negative 6 power? So remember, as I mentioned a while ago, the easiest way to find an upper bound for your error is just figure out the first term you're going to drop. And so what I'm going to do right now is just plug in 0, or in this case to 0.1. By the way, if you plug in 0, they're all 0. So it's all about 0.1. So you want to plug in 0.1 so that the error or the value is less than 10 to the minus 6. So let's try x to the 7 over 7 times 3 factorial. So let's plug in 0.1 on that one. I hope my calculator is clear. Okay, so it's 0.1 to the 7th divided by parentheses 7 times 3, and I have to go to math, probability, factorial. So it's definitely less than 10 to the negative 6. So, but that doesn't mean it's the first one you drop. So this one is 2 times 10 to the minus 9. Let's try the previous one, right? So I'm going to try this as the least amount of terms as possible. So we're going to go ahead and try this next one, right? So the x to the 5th over 5 times 2 factorial. So I try it again, right? So I need to change the 7 power to 5, this one to 5, and this one to 2. So this one is 1 times 10 to the negative 6. Okay, which is equal to this one. Okay, so now since you want it to be strictly less than, then that means this is the first one you drop. and you're keeping the first three terms. So the first three terms is what you're keeping, and this is the first one you drop. So which means the value of this is approximately x minus x cubed over 3 plus x to the fifth over 5 times 2 factorial from 0 to 0 0.1. Oops, 0.1. Okay. And then just evaluate, right? So now you're going to plug this in into your calculator, right? And see what the value is. Okay. So it's 0.1, okay, minus 0.1 to the third divided by 3, okay, plus the previous one, which is that one, right? And so press enter. And so the value is 0.099667. 1, 2, 3, 4, 5, 6. So it's since it's to the sixth power, right? So basically it's um, like 5 decimals. And so it would be approximately this 0.099668. And that is your answer. Oops. Okay. Any questions on that? By the way, to double check and see if we did it right, okay, your calculator has an integral button or integral function. Okay, so if you click on math, right here it says function integrate. So you're going to integrate a function. So it's e to the negative x squared, right? Comma x. So you're integrating x from 0 to 0.1. And notice it's almost the same answer. Any questions on that? Any questions on it? Okay. So you can use this to find, the value, right? So I want you to try one. Okay. So let's try another one. Okay. So example number 4. So I want you to approximate. So evaluate. This one has no integral. So you're not going to use any integral. So this one, I just want you to evaluate cosine of 0.5, okay, such that the error is less than. Let's change the error to something else. Let's do 10 to the minus 7. So the first thing you want to do is write out the power series for the function you are using. So in this case, the power series for cosine. So cosine x, right? So you do have to write the terms because you are going to try to figure out where to cut things off. So cosine x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and then just continues on. Okay. And then now you're going to plug in 0.5 for x. And so now what you want to do first is figure out, okay, which term are you going to drop first? So how do you know which term to drop? You're going to plug in 0.5 and see which one is less than 10 to the minus 7 power. Okay, so go ahead and do that, okay, for this problem. Is it working now? Is it working? Okay. I had my mic turned off on this one. Okay, that's fine. All right. So, did anyone actually try it? Right. So, so did anyone get to a specific degree? So, what degree was it? Okay. All right. So, if you don't have it, so let's go ahead. Oh, eighth. Okay. So, someone did it eighth. All right. So, let's try it out. So, I'm trying a two right now. So, so I'm trying the second degree one. And so, when I do, you get 0.125, which is definitely not less than 10 to the minus 7. So someone said 10 to the 8th. So let's try x to the 6, right? So I'm going to jump a bit because someone said um, the 8th power is the one that works. So let's do the 6th power first. So it's 0.5 to the 6th power divided by 6 factorial. I should just press second enter. So this one is 2 times 10 to the minus 5. By the way, that's what that E means. It's a scientific notation. So E means times 10 to the minus 5. So this is definitely not less. Okay, so let's try the 8th power. So let me just press second enter. And so by pressing second enter, it retypes everything. And so 8. So it's now 9 times 10 to the minus 8, which is definitely less. So this is the first one you drop. So you're dropping x to the 8th over 8 factorial, and you're keeping the first 4. So this can now be approximated. So cosine of 0.5 is approximately 1 minus 0.5 squared over 2 factorial plus 0.5 to the 4th over 4 factorial minus 0.5 to the 6 over 6 factorial. So now go ahead and put that in your calculator and see what you get on that one. So it's 1 minus 0.5 squared. Plus 0.5 to the 4th divided by, oh, I forgot to put 4. And then minus the 6th power. And so it's 0.8775824. So since we're trying to get it to like um, the seventh sort of position, right? It's 10 to the minus 6, but basically to the 7th position, you're gonna round around there. So so it will be approximately 0.877582 and then 5. Okay, the 7th decimal. Okay, and now just to show you that that is the correct answer, right? So let me make sure I am in the right mode. I am in radian mode. So now just do cosine of 0.5, okay? And it should be close to our answer. And notice it's basically the same thing. Questions on that? Yes. The integrating part, the one we did a while ago, was just to use the correct power series. So over here, we did not use the power series for e to the negative x squared. We used the power series for the integral of e to the negative x squared. So the integration is just an application of it. This is another application of that, right? So this is finding the value instead of you obviously using your calculator, right? You're using polynomials to find the value of your function, okay? In this case, we're plugging in 0.5 into our polynomial function or polynomial approximation. And that will give you a similar value to cosine 0.5. Okay. Question. So I can do this to any one of our power series. So for example, I have to flip over. One more. So I can use this to any one of these, right? So for example, I could ask you, what is e to the 0.1? And so you're plugging in 0.1 on here, okay? So you can use this, essentially the polynomials here, to plug in a value for x on each one of these problems. Okay. Questions? Any questions on this? Let's try one. Let's try this one. Okay, so let's try this. Okay. Now, another way to word this problem. Right. So over here, I ask you to find cosine of 0.5. Sort of a similar problem, okay, but it's sort of worded differently, is something like this. What degree polynomial? Should be used to evaluate ln of 1.2, okay, such that the error is less than 10 to the minus 4. Okay. So we're using the ln 1 plus x polynomial, right? So we're using the ln 1 plus x polynomial. And if you forgot what the ln of 1 plus x is, right? It's this one, right? Maybe I should tear this off, and so that way we always have it. That way I don't have to go flip back and forth. So it would be the x plus x squared over 2, x cubed over 3, x to the 4th over 4, x to the 5th over 5, dot, dot, dot. Right, so this time there's no factorial because it doesn't have one of those in the formula. By the way, on this problem, what is x? What number are you going to plug in
1.2.
on this problem?
1.2.
So I want to find ln of 1.2. Okay. What is, and this is the power series we're using, right? This is the power series we're using. So what should be x if I'm trying to find ln of 1.2? It's 0.2. Right. So that is what you have to plug in for your x, right? So you're not plugging in 1.2, you're plugging in 0.2 because this is the power series. It's ln of 1 plus x. And since the value you're supposed to have in the logarithm is 1.2, so in terms of 1 plus x, x is 0.2. So 0.2 is what you're plugging in. Now, the difference between 4 and 5 is the answer, right? So for number 4, the answer is the actual value, right? So this is our answer, okay? For number 5, the answer is not the value. The answer is what degree are you using? So over here, the answer would have been 6 because that's the degree that we kept as far as our polynomial approximation was concerned. So over here, all I'm after here is what degree am I keeping? Okay, so go ahead and do this. So it's the same problem, but the answer would be just the degree, not the actual value of the function. So go ahead and try it again. Okay. So try this problem. All right, so does anyone have the answer? And so you plug in 0.2 into each one of these terms, and then find the one that's less than 10 to the minus 4. The third degree. Okay. So let's try this out, right? So let's try with the second degree first, right? Just to show you. So if you plug in the second degree, right? So 0.2 to the second over 2, right? And so that would be 0.2 squared divided by 2. And that one's 0.02. Okay. And then try it again, this time to the third power. So 0.2 to the third divided by 3. Sorry, press times. The third degree is not it, because that's 0.2. Well, I guess to the fourth power, I have to do. Okay, I'll try this out. So the third degree over 3 is 0.0026. So that's still not less. So let's try it again. Let's try the fourth. Okay. Now you're gonna say that's no, it's not the fourth degree. Because this is the fourth, right? So the fourth is right now, the one I plugged into my calculator. So notice you're gonna say, oh, it's e to the minus 4. That's 10 to the minus 4. Well, remember, look at the number in front. The number in front is 4. So that's 4 times 10 to the minus 4. This 10 to the minus 4 has a 1 in front. It's 1 times 10 to the minus 4. So this is still not less. So you're gonna have to do it again. So 5 and then 5. And this is now definitely less than 10 to the minus 4. So which means the one you drop is the fifth term. So you're dropping the fifth one and you're keeping the fourth degree polynomial. So now the question is, what degree polynomial should be used to evaluate 10.2? So you say the degree is equal to 4. I guess the answers were, I guess, depends on what was asked. So you say degree is 4 and you drop the fifth. So yes. Okay. Any questions on these? Any questions on this? Now, there are a couple of things I do want to go over, or at least sort of run through what we just did. Okay. So, but any questions on what we've done so far? Okay, so the first one I want to go over is this last question that we did. Another way to ask the same question is, instead of saying what degree, they're going to say how many terms. So how many terms are you going to use to approximate your natural log of 1.2 so that it's less than 10 to the minus 4 as far as your error is concerned. So for us, that would be 1, 2, 3, the fourth term. So the fourth term and the fourth degree, they're equal just because that's how your power series work. Now note, if I ask the same question on number 6, the answers are different. So if I ask you, how many terms are you keeping? Well, based on what we found, we're only keeping 3 terms. But if they ask you what degree polynomial are you using, well, in this case, you're using the fourth degree. So notice the answer is different. Okay, so make sure you read the question on what is being asked. So how many terms or what degree? So you're gonna have to pay attention to that. Okay, questions on that? All right, now the other thing, okay? So it's cosine of 0.5. Now, notice that we use cosine x, which is the Maclaurin, which means the center was 0. If this was cosine 3.2, okay, so cosine 3.2 as a value. Now, 3.2 is closer to pi, which means if I use a Taylor series in which the center is pi, I will end up using less terms than if I use a Maclaurin series whose center happens to be 0, which is this one. So be careful with that, right? So especially if you have the freedom to choose your own center, then you want to use a center that will be closer to where you're evaluating. Now, that's why on the test are more likely going to say Maclaurin on there. That way, everyone is using a center of 0. So, for example, even if I give cosine 3.2, I will say, oh, use a Maclaurin one, which means you're going to have to use this one as your polynomial. Okay, so you cannot use a center that is pi, even though it is closer. Okay. Any questions on this? Any questions on it? Okay. All right. So this is a perfect time to take a break. So 10.10 is done. This is it. This is it for 10.10. We're actually done with this one. Okay. And so the next one will be we're going over what's going to be on your test before we start chapter 11. So let me stop my recording.